let's talk about something that makes up nearly 70% of our entire universe. The crazy part? We can't see it, we can't touch it, and we can't measure it directly. This invisible energy is literally pushing our cosmos apart, and figuring out what it is will decide the ultimate fate of, well, everything. This is the story of dark energy.
So here's the core of the mystery. For the longest time, we all figured gravity was the boss on a cosmic scale, constantly hitting the brakes on the universe's expansion. But when we looked, the exact opposite was happening. It's kind of like throwing a ball up in the air and watching it just accelerate into space instead of falling back down. Something out there is overpowering gravity, pushing everything apart faster and faster.
So how did we even get to this point? Well, this whole thing kicked off with a discovery that was just completely shocking. An observation so weird, it seemed to break the laws of gravity as we knew them. Scientists were peering deep into space, fully expecting to see the universe's expansion slowing down. What they found instead turned everything on its head.
And that brings us to this core idea: cosmic acceleration. Instead of gravity pulling everything back in after the Big Bang, the expansion is actually speeding up. This one observation just threw a giant wrench in the gears of cosmology, because nothing in our physics could explain it. We needed a new piece to the puzzle.
So, that new puzzle piece, the prime suspect behind this runaway universe, has been given a name. And honestly, it's a name that perfectly captures just how much we don't know about it: dark energy.
Now here's the key thing to remember. Dark energy is still just a hypothesis. It's not something we've ever held in a lab. It's the best explanation we have for why the universe is expanding the way it is. Really, it's a placeholder name for the mysterious something that's causing this effect. But what on earth could it actually be?
Well, right now, physicists have two main ideas. On one hand, you've got Einstein's old cosmological constant. This is the idea that empty space itself has some kind of built-in, unchanging energy that's always pushing things apart. It's static. On the other hand, there's a wilder idea called quintessence. This would be a totally new dynamic energy field that could change over time and space, maybe even a fifth fundamental force of nature. So that's the big question. Is dark energy a constant, or is it changing?
So, if we can't see this stuff, how in the world do we know it's even there? How can we possibly measure its effects? Well, astronomers have become cosmic detectives, and they've found some incredible clues scattered across the universe that all point to this invisible force.
The first huge clue comes from these amazing cosmic fireworks, Type 1a supernovae. Here's the cool part. These stars always explode with pretty much the exact same brightness, so we can use them as standard candles. Think of it like a row of 100-watt light bulbs stretching into the distance. By seeing how dim they are, we can tell exactly how far away they are. And it was by looking at these supernovae that astronomers first realized, whoa, they're farther away than they should be. The universe's expansion must have sped up. Okay, our second clue is something called baryon acoustic oscillations. It sounds complicated, but just imagine giant sound waves, or ripples, spreading through the super dense early universe. As the universe expanded and cooled, those ripples basically froze in place, leaving a pattern in how galaxies are clustered together. This gives us a standard ruler. By measuring the size of these ancient frozen ripples at different points in cosmic history, we can build an incredibly precise map of how the universe has expanded over billions of years.
Now, to really crack this case, we need way more data. And that means building some of the most powerful and sophisticated instruments humanity has ever designed. So let's meet the high-tech detectives who are on the case right now.
And this is no small operation. This is a massive global scientific mission. You've got major players from the European Space Agency, like their Euclid mission, and from NASA with the incredible Nancy Grace Roman Space Telescope. And that's not even counting the huge projects on the ground, like the Dark Energy Survey, the Rubin Observatory, and DESI. They're all working together to map our universe like never before.
Just take a look at one of these cosmic detectives. This is the Euclid Space Telescope. Its whole reason for being is to create the largest, most accurate 3D map of the universe ever made. It's designed specifically to chart the influence of dark energy and its mysterious cousin, dark matter.
So how do these telescopes hunt for something that's totally invisible? They use a few clever tricks. One is called weak lensing, where they look for the tiny ways that the light from distant galaxies gets bent by the gravity of all the unseen stuff in between. Then there's galaxy clustering, which is all about mapping those ancient standard rulers we talked about. And of course, they run massive supernova searches to find thousands more of those standard candles. Put it all together and you get a ridiculously precise history of our universe's expansion.
But this isn't just about solving some abstract physics problem.
This quest is so much bigger than that. The answer to what dark energy is, well, it holds the key to the ultimate fate of our entire universe. What we find will literally write the final chapter for the cosmos.
I just consider one of the more dramatic possibilities. What if dark energy isn't a constant? What if it's some kind of phantom energy that actually gets stronger over time? If that's the case, the consequences are just staggering. It could lead to something called the Big Rip, where the expansion gets so powerful it would eventually overcome everything. First, tearing apart galaxies, then solar systems, then planets, and finally, the very atoms that make us up.
But hey, that's just one terrifying possibility. The truth is, we are at a genuine fork in the road for physics. All this new data from these missions might just confirm what we think we know. Or it could force us to tear up our textbooks and completely rewrite our understanding of the universe. The stakes just couldn't be any higher.
And in the end, it all comes down to this one fundamental question. Is dark energy a fixed, constant property of space-time itself, like Einstein's old idea? Or is it something new, something dynamic and evolving? Answering that question is the whole point of these multi-billion-dollar missions. And whatever they find, the answer is going to forever change how we see the universe.